Very good afternoon to all of you. Now, whatever we have learned in lecture number 3, part number 1, we'll do some numerical practice on that. So, first I have taken this question. You can write this question in your notebook. A load of 5 kN is raised by means of steel wire. Find minimum wire diameter required for safe stress of 100 megapascal. Okay, so there is a load of 5 kilonewton. This is raised by a steel wire. So this such type of question you have already solved in strength of material. If 5 kilonewton wire load is hanging with the help of wire, then obviously the tensile load in the wire is 5 kilonewton. So W tensile in nature is given 5 kilonewton, and we have to calculate the wire diameter. Let the wire diameter is D, so D is unknown. And safe stress, the safe tensile stress which can induced into the wire is 100 megapascal. We are very well aware that megapascal is nothing but Newton per millimeter square. So this is 100 Newton per millimeter square. So this is in Newton, then we'll keep this also in Newton. So this will become 5000 Newton. So we know that the stress induced. Now let this wire diameter is asked. So it's area, the cross section area of the wire or wire area भी लिखेंगे मैं सिर्फ इसको. A is pi by 4 d square. So the stress induced, we know that stress induced is always load upon area. The unknown dimension is in area, so I'll take area here. Area is equal to W upon sigma T. Notice area, this is pi by 4 d square is equal to, how much is W? We'll put the values, 5000 divided by sigma T is given 100. Now we'll keep all the unknowns one side. So d square will be 4 upon pi into 5000 divided by 100. Now we'll calculate. D will use the calculator. With the help of two brackets, we will solve this. 4 into 5000 divided by pi into 100. Answer is 63.66. We will take the square root of answer, 7.97. 7.97, and this will be in millimeter because all the length dimensions are in millimeter. We can round or we can take this as 8 millimeter. So the wire diameter will be 8 millimeter. 8 millimeter can bear this much load easily because the material strength of the material is 100 megapascal. So in this style we solve the numerical like this. Now if you have understood, we will take the second numerical. This is also on the tensile stress. We will take the second numerical. A cast iron lint as shown, means the diagram is given in the question, is required to transmit a steady tensile load of 45 kilonewton. Find tensile stress induced in the linked material at section AA and BB all dimensions are in millimeter. It is given that all dimensions are in millimeter. Now the diagram of the link is given like this. The section AA is here and section BB is here. The depth of this link is given 45 and hatching, with hatching the dimension is given, then this will be the thickness. So this is given 20. Now the side view of this link is also given in the question. I'll draw the side view. This is 75 and this is 40. This width is 20. This is given, this side view is given for section BB. So this is the diagram given. A cast iron link as shown is required to transmit a steady tensile load. The load is in the nature of tensile of 45 kilonewton. So by reading this question, you come to know that W is given 45 kilonewton. W is given 45 kilonewton. Find the tensile stress induced in the linked material at section AA and BB. All dimensions are in millimeters. So all the sectional dimensions are given in the diagram only. Okay. We have to calculate the tensile stress. So tensile stress at section AA and tensile stress at section BB. Now we know that the tensile stress is nothing but the load upon area. At whatever which particular section you are calculating, we have to put the area at that section only. Area of that section only. So we'll calculate first the tensile stress at section A. Now for section AA, what will be the cross sectional area? Okay. So from diagram we come to know that the cross sectional area at AA will be nothing but a rectangle because the height and the width is given. So the cross sectional area at section AA will be 45 into 20. So we'll calculate sigma T at section AA. So sigma T will be the load for section A and B both are same because it is acting on complete link. So sigma T is equal to load upon area at section AA. So load is 45 kilonewton. If we convert this into Newton, it will be 45,000 Newton. So we'll keep in the Newton. So sigma T will be in megapascal. So 45,000 divided by area at section AA is 45 into 20. Now again we'll take the calculator and solve this. 45,000 divided by 45 into 20. It is 50. So the tensile stress induced at section AA is 50 megapascal. If the load is in Newton and dimensions are in millimeter, then sigma T will be 50 megapascal. In the same style, we will calculate the sigma T at section BB. Now section BB, already the section is given in the question. So it becomes very easy to attempt this because we can calculate the area at section very easily. The area is actually at section BB, it is a hollow ring type. And when we see the side view, because the tensile stress will induce into the side view in that section. So the section is looked like this. The big rectangle minus this small rectangle will get this area. So sigma T at section BB will be sigma T is equal to W upon area at section BB. Now area at section BB will be, the load is 45,000 and area at section BB will be 75 into 20 minus 20 into 40. Can you see this? 75 into 20 minus 20 into 40. The big rectangle minus this small one. That small one is 20 by 40. It becomes 45,000 divided by, if we take the 20 as common, 75 minus 40 into 20. Take your calculators and solve this at calculator. 45,000 divided by 75 minus 40 into 20. You can use the brackets in order to reduce the mistakes. 64.28 megapascal. Now you can see the load is same for the entire link, but as the dimensions, the cross-sectional area is changing at different places, so the tensile stress induced at different section is different. So tensile stress induced at section AA is this, and tensile stress induced at section BB is this. Now we'll take the next numerical. It is based on punching shear. We revise the formula required for punching shear because in previous part 1 I have already explained the punching shear. So third numerical is calculate force required to punch a circular blank of 60 millimeter diameter in a plate of 5 millimeter thickness. Ultimate shear stress of plate is 350 Newton per millimeter square. 350 Newton per millimeter square. Calculate force required to punch a circular blank of 60 millimeter diameter in a plate of 5 millimeter thickness. Ultimate shear stress of plate is given 350 Newton per millimeter square. The tau for the plate material is given 350 Newton per millimeter square. So you are very well aware with this diagram. The thickness of the plate is given. The thickness of the plate is 5 millimeter. So the T is given. Thickness of the plate 5 millimeter. Now we want to punch a hole of diameter 60 millimeter. Now to punch this hole, we need some force on the punch, on the drill. That load, that force is unknown. We have to calculate the force required to punch a circular hole. So W is unknown. Now we know that for punching shear, the area involved in punching is nothing but the cylinder which is cut, the surface area of the cylinder which is cut from this plate, and that area is nothing but pi d into T. That will be pi into diameter of the hole is 60 and thickness of the plate is 5. So pi into 60 into 5. Now we know that the shear stress, whatever will be the stress, the formula remains the same, load upon area. So the load, the force which is going to punch this hole, that divided by area. W is unknown. What do? We'll take the unknown on one side. So we'll change the side of the rest. So W will be on one side. Now A will change, when the A will change its side, it will become tau into area. Tau into area. Now the tau is 350 megapascal into the area is pi into 60 into 5. You calculate this, you put this in calculator, you will get how much force, how much Newton force is required to punch this hole. So 350 into pi into 60 into 5. The answer is 329.86 into 10 raised to 3. 329.86 into 10 raised to 3 Newton. And if you want to write it in kilonewton, then it will be 329.86 kilonewton. So this is the final answer. The force required to punch this hole is this much. I expect that you all have understood all these three numericals. Now we'll take the one numerical from crushing stress. Question number 4. Question number 4, numerical number 4. Two plates of 16 millimeter thickness are joined by a double riveted lap joint. Rivets are 25 millimeter in diameter. Find the crushing stress induced if maximum tensile load on joint is 48 kilonewton. 48 kilonewton. So the question is, two plates of 16 millimeter thickness are joined by a double riveted lap joint. Means there are two rivets. Rivets are 25 millimeter in diameter. Find the crushing stress induced if maximum tensile load on joint is 48 kilonewton. I have drawn this diagram various times before also, but I have shown only one rivet. Now these are two plates and the thickness of each plate is 16 millimeter. The thickness of each plate is 16 millimeter. Now this is joined with the help of two rivets. So I will draw two rivets. One rivet, two rivets. So there are two plates joined with the help of two rivets. Now the tensile load acting these two plates are of 48 kilonewton. So the W is given 48 kilonewton. Now we have to calculate the crushing stress induced. How much the crushing stress will induce into the rivets. We know that the area involved in crushing is nothing but the projected area of the two matting parts. The projected area. We know that the area in contact of a single rivet, this rivet number 1 to this plate, we have to calculate for one pair of surfaces. So one plate, one rivet. So one plate, one rivet, the area is this, the projected area for one plate, one rivet is this rectangle, but here there are two rivets. So for the same plate, we will do the analysis for the same plate, the area is this. So this is the area, projected area. If you see the front view, actually this area in contact is cylinder, but when we draw the projected view of a cylinder, it is nothing but a rectangle. Now the dimension of this rectangle, these two rectangles, will be the diameter. This dimension is nothing but the diameter of the rivet. The diameter of each rivet is given 25 millimeter, and this dimension, vertical dimension, is nothing but the 16 millimeter, because of the thickness of both the plates are given 16 millimeter. Now this is 2 times because there are 2 rivets. So for one plate there are 2 rivets. So we'll do this analysis for one plate. Now we'll write down the given data as well as the unknowns. The W is given 48 kilonewton. We can convert this into Newton. 48,000 Newton. The area under crush for one plate. एक प्लेट के लिए एरिया अंडर क्रश कितना है? It is D into T. The diameter of the rivet is 25 into thickness of the plate is 16. Now for 2, include this area under crush for one plate. Since there are 2 rivets in one plate, so we'll write the area 2 into D into T. So 25 into 16 into 2. This is the area under crush for one plate. So we have to calculate the crushing stress. Whatever will be the stress, the formula remains same, load upon area. So the stress induced in crushing will be load, which is going to induce the crush, divided by the area under crush. So load is 48,000 Newton, divided by area is 25 into 16 into 2. So sigma Ck, the crushing stress induced will be, use your calculators, 48,000 divided by 25 into 16 into 2. It is 60 megapascal. So in this style, we solve the numerical. This is the numerical asked on crushing stress. Now we will take one more numerical on bearing pressure or bearing stress. Now in this case it was only crushing. We are very well aware because we know that these rivets are will not have any relative motion between the plate and the rivet. Now we will take the next numerical, question number 5. Question number 5. A journal a journal 25 millimeter in diameter and supported in sliding bearing has maximum end reaction of 2.5 kilonewton assuming allowable pressure 5 Newton per millimeter square. Find length of sliding bearing. The length of sliding bearing. So this is the question. A journal 25 millimeter in diameter and supported in sliding bearing. Journal you can consider like a shaft, has maximum end reactions of 2.5 kilonewton. Now end reaction is given, but with the help of unit we can easily recognize this is the load, this is the force acting on these two, support and the shaft. So assuming allowable pressure is given 5 Newton per millimeter square. Since there is a shaft and the bearing, so this will be obviously the bearing pressure. Find the length of sliding bearing. So we can draw. Suppose this is a journal. This is the journal and this is supported in sliding bearing. This is supported in sliding bearing. Then reaction, the force acting this, which is going to produce the bearing pressure, is 5. You can draw that over here. So W is given, 2.5 kilonewton is given 2.5 kilonewton. The diameter of the journal is given 25 millimeter and the length of this sliding bearing is, this is unknown. The length of the sliding bearing is unknown. So I'll write the given data and the unknown data. So W is given 2.5 kilonewton. Because of this W, the bearing pressure is going to induce. You can write 2.5 into 10 raised to 3 Newton. The bearing pressure, the allowable bearing pressure is given 5 Newton per millimeter square. The diameter of the shaft is given. The diameter is 25 millimeter and length of the bearing is unknown. Now we know that when there are two parts in contact with each other and if there is the relative motion between them, obviously when there is the bearing, sliding type of bearing, there will be the motion, relative motion between them. Then the projected area of those two will be this. The area in contact is cylindrical, but the projection of the cylinder is nothing but a rectangle. So the projected area, this is that projected area. This projected area is nothing but diameter into length of the bearing. So the diameter and length. Diameter is 25 and length is unknown. So the unknown dimension is in area. Now we will know that the bearing pressure, whatever will be the pressure or stress, the formula remains same, load upon area. The load in reaction is W divided by the area under bearing pressure. So the load is 2.5. Now we'll do one thing, we'll change first the side. Since the unknown is in the area, so it will change the side of area. Area will be equal to W upon bearing pressure. Now W is 2.5 into 10 raised to 3 upon bearing pressure, allowable bearing pressure is given 5. We'll get the area. Area is 2.5 into 1000 divided by 5. Area is 500 millimeter square, but we don't have to calculate the area. We have to calculate the length. Now the formula for area. Area is 500 and area is nothing but 25 into length is equal to 500. So length will be 500 divided by 25. 500 divided by 25, it is 20 millimeter. So the length of the bearing will be 20 millimeter. Length of the bearing is 20 millimeter. This is the final answer. Length of the sliding bearing. Such types of question may come from the, or this is under the category of simple numericals. We can very easily calculate. We have to use these as the small simple steps in large numericals. So you all must understand all these 5. I have taken very basic numericals, 5 numericals very well. If you have any doubt, then you can ask me. Now whenever you will see all of these by 2 videos, then you put some comment, some response at least, so I'll come to know that these many students have checked this. So, thank you.